All right, so we don't waste any time. Let's get started. Who has questions? Yes,
Anytime during class, would you mind doing a visualization of quicksort?
visualization, quicksort. Sure, we can do that. Yeah. I would say, I don't want to answer that. You should know everything that we've covered. It is unlikely that I will put something in an incredible amount of detail based on what we did on a linked list. I'd like to differentiate what we do for assignments from what we do on exams to whatever extent that I can, or at least abstract it a bit, so it's not as directly implementation of what you've already implemented. So I would know the general why. Why does what we do on an array list not work on a singly linked list? But I don't think it's important to know the exact implementation details of the linked list. All right, quick sort. I did it, right? Do an array of size 6 because that's how much room I made. Who wants some numbers, or who wants to give me some numbers?
17.
Always a good start.
22.
-3.
0.
27.
Cool. Just like I would think, about half the numbers have a 7 or a 3. For some reason, those are really popular numbers. All right, so how do we want to handle this quicksort? What do we want to do with it? So there are lots of ways to make the quicksort work. So we're going to go through this in ArrayLand because that's how it's typically done. We implemented this on our singly linked lists because we had done that. My goal with the entire quarter is to give you a project that you can show off to people to say, hey, I did all of this work. And yes, quicksort is an absolute pain with singly linked lists. But in general, this is done with either a doubly linked list or an array, just to make your life a little bit easier. So I'm going to do it like it's on an array, because if I have you implement or show anything on the exam, it's going to be either with an array or with a doubly linked list where you can access a previous. So where do we want our pivot? We want it to be the low, we want it to be the high, we want it to be an element in the middle that we swap to the low or the high. Those are the 3 common ways that it's done.
Median.
Median? Is that what you said?
Yeah.
Okay, yeah, we can do that. So if we're gonna pick the pivot, let's take the middle element. So we're gonna integer divide the size. Or if we really want to get the middle element toward, do we want to bias it by the left or by the right? For this, I think it'll make more sense to bias it by the left. So we'll take the size -1, that quantity over 2, and that will identify this element as our pivot. So how we would typically do this is we're going to swap what's in the first position with what's at the pivot's location. So the pivot is at that location. So now we know the pivot is here. The reason you would do something in the middle is it just gets around lists that are either sorted or unsorted. Because that is a common way that lists show up. If you pick a pivot that is in the middle and then swap it to the end, then you can sort lists that are in order or in reverse order without seeing that quadratic worst case behavior. All right, so knowing the pivot is 22, we're going to set a low pointing here, we're going to set a high pointing here. And the goal now is for low to point at something that is larger than the pivot, and for high to point to something that is less than the pivot. So, is low greater than the pivot? No, bump it up. Is low greater than the pivot? No, bump it up. Is low greater than the pivot? No, bump it up. Is low greater than the pivot? No, bump it up. Is low greater than the pivot? Yes. So low ends up pointing here. High is still pointing here. So is high less than the pivot? No. Is high less than the pivot? Yes. Since they have now crossed over, we know that since we're starting at the low end, we want to swap the pivot with what the H is pointing to. If we started at the high end, then we would be swapping with L. So you swap with, when it has to actually cross over and not be pointing at the same location. That's a common mistake. Once they've actually crossed over, you're going to swap with, if the pivot is on the low end, think about the other one, you're going to swap it with H. If the pivot starts at the high end, you're going to swap it with L. So we're going to swap in the 22 with the 0. This locks this in place. And we're going to make recursive calls on this subarray and this subarray. So we'll follow this algorithmically rather than seeing that the right is a really easy case and just solving it. We're going to start with the left. So quicksort is going to work on this. Where's the pivot located? That it's going to be the middle element minus 1 over 2, or sorry, the length minus 1 over 2. So if the length is 4, 4 minus 1 is 3. 3 divided by 2 is 1. So looking at index 1. So we're copying just this section at the moment. But when we identify the pivot here, we're going to swap them. So here's the pivot. Here's our low, and here's our high. Low always starts one position after the pivot. High always starts at the end. If we were using the pivot at the end, then low would start at the beginning, and high would start the position before the pivot. So we want low to point to something greater than the pivot and high to point to something less than the pivot. Let's start with low. Is 0 greater than the pivot? No. Is 17 greater than the pivot? Yes. So we will point L here. Starting with H. Is -3 less than the pivot? Yes. We've identified low is still less than high. So we swap these elements. We're going to take the 17 and move it to the end, and the -3 and move it there. As we do this, we can bump up L and bump down H. Since we know now that they're doing what they're supposed to. Now they've crossed over, since we bumped them over. So we want to swap the pivot into place where H is. So we're going to take 4 and swap it with -3. This locks this in place. And in fact, what I'm going to do to draw this is I'm kind of just going to draw this 4 back up here. Say, we've locked this in place. We know that that's where that goes. So we're actually modifying the same array this whole time. There's no duplicates or copies. I'm just visually making these copies. So really what the state of the array is after this is complete is this is -3. This is 0. This is 17. And this is still 27. What's fun is it's already sorted, but there's no way quicksort would know that quite yet. So we're going to, at the end of this, make recursive calls on the left side and the right side. So we're going to start with the left. We can set the pivot to be here. We can set low and high to be there. So let's actually just make that copy. So let's ask the question now, okay, this is the pivot. Is low greater than the pivot? Yes. Is high less than the pivot? No, so we're gonna bump down H. Now they've crossed over. So we want to swap the pivot with where H is pointing. Hey, look, H is pointing exactly where we want the pivot, right where the pivot already is. So we swap -3 with itself. And there is no left, but there is a right. So now we know this is in place. But we are going to make a recursive call on the right. As we do this, we see it's a base case. It's an array of size 1. We can just return it. At that point, we know it's in the right place. So that finalizes this as in place. We return to here, there is no right. We return to here, there was a right. We call on the right. That's size 1, so we just return, this is locked in place. We finish the left call now for this, so we can make the right call. Since that's also a base case size 1, we return and lock it in place. So now we know for sure, we have proven via the quicksort algorithm that this array is sorted. Yes. So yeah, I didn't actually go over this in class, but it's the most commonly used application of it. It does not actually matter where your initial pivot is. It could be at the low end, it could be at the high end. Most commonly in an actual implementation, it's somewhere in the middle, and you swap it either to the low or the high. And that just gets rid of that quadratic behavior if the list is already sorted, or if the list is reverse sorted, because then you're going to be picking a pivot that's not the highest or the lowest value. You're going to be picking something that's in the middle. And since sorted lists and reverse sorted lists are fairly common in practice, that just makes it less likely that quicksort uses its quadratic worst case behavior. So it doesn't actually matter, it doesn't change the algorithm at all. It just says that that worst case behavior is less likely given what we are likely to see with the structure of an array that's passed to us. Or structure of a list, I should say.
So we do all the left partitions prior to returning back and then doing the right partition?
Yes, yeah, it's recursive in nature. For if you look at it in code, basically you are identifying the pivot's location, and then you call the left, and then you call the right. So the left has to fully evaluate in a particular perspective before you call it on the right. So yeah, the calls would be identify pivot. Then quicksort the left. And then quicksort the right. So we have to return from quicksorting the left before we begin quicksorting the right. And in this case, quicksorting the left was a much larger problem than quicksorting the right. So we had to fully evaluate and sort the left side before we started with the right side. So we did all of this work before doing this work, even though this work looked really easy. From a computer's perspective, it doesn't do that high level analysis. There's really no benefit to that analysis in terms of the actual execution time. As humans, we like to do the easy things first. From a computer's perspective, every single instruction that at least is something like this is approximately equally taxing.
Take time away from a couple of questions. There's a specific sequence I was struggling with.
Yeah. Yes.
1, 2, 7, 4, 6.
1, 2, 7, 4, 3, 6. Okay, so that is your quick sort.
Yeah, that's the
Yeah.
list I need.
Yeah. Let's take a look. So we do this, we identify a pivot here, we swap the pivot to here. We're going to put a low and a high So low here. High here. Low is gonna move all the way past high because it's not gonna find anything that is greater than the pivot. So it's gonna swap over pointing here. If we started the pivot on the low end, we're gonna swap it with H. So this becomes a 6, this becomes a 7, 7 is locked in place. Recurse on the left. Recurse on the right, size 0, that's another base case that just does nothing. So let's recurse on the left. This is gonna be something that looks exactly the same, where the pivot is the largest value. So we have our pivot, we have our low, we have our high. And we're gonna see that low moves all the way to the end again, so this 6 is gonna swap with the 3. That's gonna lock the 6 in place. We still have 2, 1, 4, so we're gonna recursively call on that. So now we take the 2 as the pivot, so we're gonna swap the 2 and the 3, since that's the halfway point biased on the left from this. Here's our pivot, here's our low, here's our high. So low already finds something that's larger, high needs to find something that's less, so that's going to point here. We're gonna swap. Then we bump up low and we bump up high. Gonna erase the arrows. Now that they've swapped over, we're gonna swap the 2 into place with the high. That locks that in place. We're gonna recursively call on the left, which is already done, that locks the 1 in place. We're gonna recursively call on the right. So here's our pivot. Since we're biasing on the left again, pivot is here, and the high and low both point at 4. Which one moves, high or low? Yeah, so low moves and moves out here. So this does create a case that we need to handle. If high is outside of the bounds of the array, then that means keep the pivot where it is.
Wait, explain that again. So wait, so the 2 arrows, right? High and low. You
Yeah.
move the low over first.
Actually, it shouldn't. Low is gonna identify something that is larger than, so it's the high that moves.
Okay.
So it's not a special case. We want to swap the pivot with itself.
And we know that because low moved to the outside wall. Sorry, high moved.
So high did not end up moving out of bounds.
Okay.
High ends up pointing at the pivot, so we swap it with itself.
Okay. Right, got it.
So I think this process still works.
Okay.
We get 3, 4, and 6 all locked in place.
All right.
So at least from my quick board work, when I move that fast, it's possible I make a mistake, but it seems like that sorted it and did everything without issue. Thanks. What else can I answer? Yeah, Yeah. yeah. Okay, hash codes for different types of variables. So integers, there's nothing that we need to do with those integers. Remember that the whole purpose of a hash code is to uniformly distribute it amongst the table. So just taking an integer and making a hash code itself, that's possibly a bad thing if the numbers are going to be less than the size of the table. So if we make a table of size 1000, but we're keeping track of student numbers in a classroom that has up to 20 people in it, we're going to end up with 0 to 19, the indices being used a lot, and everything from 21 to 1000 not being used until we have collisions in 0 to 19. So we would be creating one very long issue. So usually something is done about this with integers. So you saw this on your homework where you went through quite a long process of multiplying numbers by things, ending up with something large, and then you ended up modding it by the table size and getting what hopefully was a uniformly distributed. So I would say you can just map an integer to an index, but be wary of the goal of all of this is just to make a uniform hash, where it's equally likely to hash into any index in the table. So that means that you may have to do something depending on the underlying structure of your integers to make sure that you get that uniform hash. So just turn that into, multiply it by a large amount, add it to something, just do something that makes it a really large number, and then mod it by the table size. And that should pretty evenly uniformly distribute where you want to make that hash, or where that hash would say that that integer goes in the hash table. For doubles, we said that we were going to do an XOR. So you're going to take, we know that a double is 64 bits, and it's broken down into basically the digits and then the exponent. But we take the first 32 bits and the second 32 bits and we XOR them. Does everyone know what an XOR is? Remember what an XOR is? Yeah. Yeah, it's your exclusive OR. So you get a 1 if one or the other is a 1. So if there's a 0 and a 1, the result is a 1. If they're both zeros or both ones, the result is 0. So you just go digit by digit and come up with a new 32-bit number. That 32-bit number is represented as an integer, because integers are 32 bits. So you take that and it's an integer, then you mod that by the table size and you're good. Does that process make sense for doubles? For strings, we're going to, in a loop, figure out the value character by character. So we're going to take the, it doesn't really matter where you start, but let's say we're going to take the last character in the string. We're going to take the ASCII code of that character, and we're going to set that. So we start with some value, some small prime, like 11 or 37. We're going to multiply that number with the ASCII code of the last character in the string. That gets you a new value. Then you're going to move to the next one, and you're going to square that one. So now you're going to take the ASCII code of the second to last digit, you're going to multiply it by itself and add it to what you have calculated so far. So it ends up looking like, let's just bring up the slide. I think the slide would have a better visual way of showing this. So yeah, you take your prime number to the 0 times s of L minus 1. So the last character in the string, you're going to be multiplying that by 1 and adding it to this initial value that you do. So the new hash is the character s of I plus 31 times the hash. So the ith character of s, just take that ASCII value plus 31 times the hash. And then you're going to continue to loop this process for each character as we move down the string. And you're just going to increase the exponent as you go. So 31 to the 0 for the last character, 31 to the 1 for the second to last character, 31 squared for the third to last character, etc. And you just basically go through this loop. take the ASCII value of that character, 31 times the hash. So you're just computing this. And that ends up being your hash, that H at the very end. 31 is some random small prime. It can be any other random small prime to be, if it's not a prime, then there are some issues with it not necessarily generating something that is evenly distributed across an array. So a prime is the best choice, but it does not matter which prime you choose. Then the last one, are there any questions about strings? Then the last one is user types. So basically, we are going to go through every field and we're going to interpret that field as the associated type that it is. So we will start with some small prime. And then for every field, you multiply the existing hash by 31, another prime that you choose. 17 is your initial value, but then 31 becomes what you multiply every field by when you add it to the existing hash. So we compute the final hash code for that. And you end up with something like this. So we have 3 fields in this object, a transaction object. There is a string who, a date when, and a double amount. So the first thing we're going to do is we're going to start the hash out at 17. The new hash is going to be 31 times the old hash, plus then we recursively call the hash code on the string. So we're going to be finding the hash value of that string using all of the logic from the last slide for figuring out the hash of the string. Then we just add that to 31 times 17. That gives us the hash after we incorporate the string. Then we're going to go to the date object. And we're going to take the old hash that incorporates the string, we're going to multiply it by 31. And then we're going to add to it the recursive definition of the date's hash code. Of course, the date is an object that has a bunch of fields. So we're recursively figuring out the hash value of that date and whatever components that date is made up of. Once we do that, we add it to the old hash value times 31. Then we do the same thing for a double. Luckily with a double, we have a process for this. We don't have to recursively call anything. We just XOR the first 32 bits with the second 32 bits and get a value. Then we multiply it by 31. Multiply the old hash by 31 and add that amount, and that becomes the hash value. So you can imagine that this gets really large. What happens if it wraps around integer.max value? Doesn't matter. We just get a really small or a large negative number, a very extreme negative number. And if we mod that by the table size, we'll still get a value in the table. So do not worry about whether we can store this hash in an integer or not. Doesn't matter. When it wraps around, that is intended and fine behavior. Does that answer the question about exactly how to handle the different hash types? Or any clarifying points that I can make with any of these? Yeah.
I guess for like an example of like a bad hash code function or a bad hashing function, would that be something, say like, if you're hashing strings, just hashing based on the length of the string?
Yeah, that would be a really bad hash. So if you're trying to identify something like an example of a bad hash, just think about something that wouldn't create a uniform distribution over an arbitrarily sized table. You could make an argument that given a particular table size, this hashing method does not evenly distribute the queries amongst those. So because of that, we will get clustering, which is bad. We see clustering even with uniform distributions if we're using linear probing. It gets way worse if we use a bad hashing function. And we want to be able to use linear probing because it's very efficient. Yeah,
So, like, doing one hashing, so we don't have this many collision.
yeah, yeah. Collisions are bad. Clustering is going to happen regardless. But with a bad hashing function, it could be really bad. Like the example from class was hashing phone numbers by area code. I'm guessing that, I don't know, raise your hand if you have a 509 area code on your phone. That's a little more than half the class. So if we were trying to hash all of this, then half of them would want to hash into the same location, and we would have a cluster half the size of the classroom right on 509, 510, 511, 512, 513, depending on the order we inserted those. So that's a worse cluster than if we just had a random uniform hash. Other questions?
So it says we need to write additional method that have functionality in the machine.
Yeah, so something that I might do is if you understand how a particular tree class works, there may be something that I would want to throw at you, like here is something else we might want to do with a tree. It's not part of the tree structure necessarily, but maybe it's a static function that interacts with a tree in some way that uses something that we talked about in order to get something back. So maybe if I wanted you to implement a depth first search in a tree, it would be a static method that given a particular query, we could then, or given a particular tree, we could then depth first search for that tree in that node. The question that would make this the easiest would be what kind of traversal would you want to do to be able to structure that depth first search? You could just call that particular traversal rather than reinventing the wheel, but it would be added functionality to a tree to do something that a tree is naturally used for. Kind of like how in prior exams, I've done that with coding problems as well, where there's been a recursion problem that you haven't seen before. So you had to draw on your recursion knowledge. Or something with a linked list that you had not coded, but utilized everything that we had written with a linked list. If you understand the linked list and the functionality of that linked list, then you can implement some use case functionality for it that uses the tools that you wrote. I will be very careful with that on this exam because I have not made the tree assignment due. So that is something that I am aware of. If you haven't gone through the work to really think through how does a tree work and the struggles that you have when implementing it, I'm not going to throw something at you that is incredibly challenging with respect to a tree. Separate chaining, that was just using a hash table to where every element of that table is now the head of a linked list. So rather than storing the data directly in the array that is the hash table, now we say if we have a collision, we're going to add it to the head of the linked list rather than try to resolve that collision by looking at other cells. So there are benefits and detriments to that. You should also know what those benefits and detriments are. So why would you use some kind of probing function and store elements directly in a hash table? Why would you use a linked list to store them? What would be an example of a scenario or a situation where you'd want to use one or the other?
Instead of moving down, moving an empty spot, it just adds it to the linked list.
Yeah, you add it to the head of the linked list, and the reason we do the head is that it's more likely that something that's been added more recently is more likely to be queried in the future. Just kind of an in general, it's less likely we're gonna look for long historical data than we are for data that is closer to the present day. You can imagine that we store in a hash table something like student records. It's more likely that we're gonna get a query from someone who graduated last year than someone who graduated 30 years ago. And that just tends to be more consistent, and that just adds to the efficiency of the structure. It's gonna be closer to the beginning of the linked list as opposed to the end of the linked list.
So that's a chain, that would be done.
Yeah. You could do it that way, otherwise it could be null, like the entire list of that element is null, so you would be checking if that particular index is null as opposed to if it points to something that is null. So again, you could do it either way, but I kind of like it as a dummy head because then you don't have to worry about checks for null. Yeah, so I didn't really talk about maps in here, so don't worry too much about maps, but I can talk about it now because it's something that you should know. So a set is, we know that there's no order and no multiplicity, but imagine storing a set as an underlying binary search tree. The set itself has no order, but the way we are going to store those elements has an order. That allows us to very quickly determine if something is in the set or not. Because we can use the logarithmic structure, the depth of a tree, to figure out whether something is in a set or not. And if we use a tree, we can easily see whether we are adding duplicates or not. Because when we try to go insert something into a tree, if we find that it's already there, we abort inserting it and it's already there. It's in the tree structure. Whereas in a list, you would have to binary search the list if it's sorted. If you added something, then you'd have to move everything out of place to be able to put it there. But if you store it in a tree structure, everything that we would want to do to a set, we can do very efficiently. So there are actually two structures that are used for sets. There's the hash set and there's the tree set. So hash tables and trees are the two structures that are used to store the concept of a mathematical set. But I honestly prefer thinking about it as a tree, even though I think the hash set is technically slightly more efficient. But there are implementations of both in Java that you can just instantiate and use. So you can make a hash set object. You can make a tree set object. A map is the concept of, if you've used Python before, it's the concept of a dictionary in Python. I'm just gonna do this so I have a little bit of board space. But that is, so there are keys and then there are values. The keys are stored as a set. So you can imagine that this is actually a tree structure, but I'm going to draw it out kind of like it's a list. This is the array-based tree where we're keeping track of where the parent is, where the children are, etc. But this allows us to store kind of an index for here's where we look for something. Each of these is going to be linked to some other object that becomes the value that you want to look up, etc. So you could have something like the key is a US state. The value, so this is the key. The value is the capital city. Capital building, capital letter. I'm gonna go with that. So that's the capital of that state. So if we queried this structure, what is the capital of Washington? You don't have to know it because it's stored in the structure. Wherever Washington happens to be in this, it would be linked to Olympia. And so when we queried this, we would be searching this key for Washington and returning whatever it maps to. So this is the concept of a computer science map. The key is stored as a set. And then this is stored as usually a list. Some kind of list. It could be an array list, it could be a linked list. It could be, these can be objects, there can be multiple that are linked to it. So when I say return to me what is at Washington, this could be an entire list of results. It could be a 2D structure of results. This is basically, you can make this any object or object structure that you want. It's just that how you find that is via a set. It's I like Python's version of a dictionary because basically you're saying, I want to know the definition of a particular word. When you flip through the dictionary, you're looking for the word, not the definition. And what you find at the location of the word is the definition. So here are your words, here are your definitions. Here's what you're using to find the information and how it's structured. And then here is the actual information that you want it to return. So that is a map. And there are also hash maps and tree maps. You can instantiate a hash map and go. You can instantiate a tree map and go. And the only difference is, how is this stored underneath the hood? Is this a hash table or is this a tree? So that answers that question, but since we didn't really get a chance to cover that too much, if there was such a question on an exam, it is no longer there. Any clarifications on this or something else we can cover?
Did you say that we won't be doing any like implementation?
Yes, yeah, you will not be writing tree code. Sorry, no. No heap code. Yeah, there's no heap code. I reserve the right to do something simple with trees. But I'm not going to do something really complicated with trees because the assignment hasn't been due yet. So I would say it's even more likely that something kind of on paper is more likely with the tree than something that is code-based. If there is something code-based, it'll be something relatively simple. Yeah, could be.
It's breadth first search typically uses the level order website, and then the other one is typically the in order.
Yeah. You're absolutely right. Depth first uses in order, breadth first uses level. We'll talk about applying those to graphs next week. It's the first time this has happened in this class where I feel like we've mostly run out of questions. People are digging for questions, which I hope means people feel like they're really well prepared. It's either really well prepared or it's so lost I don't know what to ask the question on. Regardless, it's one of the extremes. Yeah.
Some applications of hash tables.
Yeah, so here are a couple of them. So if we want to be able to store anything in a set, that is an example of that. Anything that we want to store in a map, The key to a map can be stored in a hash. Passwords are very frequently hashed and then stored as a hash, and that way if something ends up, if you become compromised or your server becomes compromised, what is possible to be stolen is the hash. That is not particularly useful for someone's password. I can't take what your hash is on my site and apply that same logic to hack into your bank. Because even if you use the same password, they might not use the same hash function. And it's only if I know the raw password that I can get around the fact that that password hashes to this on this site, this password hashes to that on some other site. If I know the password and you reuse your password, then that's a problem. But if I just know that you hash to location 22 in a hash table that stores that, then that doesn't do me any good. So that's another example, and really anytime that you want to store something that is uniformly distributed. And you want to have a place to store that in. Let's go with a general one. So when you have a large possibility space, and you need to take that large possibility space, that's a really weird smiley face. And you take that large possibility space and you try to map that onto some limited storage. Because we don't have infinite storage. So this could even be something like a ticket number and a seat. This could be anything where there's a large possibility space and limited storage. Whenever you have this generic concept, you can implement a hash table as a way to store this in that. We still can't store more than this at a time, but it allows us to take this large possibility space and store it here. So something like the words of a book. We saw that in our slide with Tale of Two Cities. Lots of other possibilities. 3 more minutes, what can I, yeah,
Go back to your password example about hash tables.
yeah,
So say it's you're creating a hash table for a password to access an account, say like the bank. The key be the password and the value be the account associated.
yeah,
with it.
so it would more likely be stored in a map.
Okay.
Because you would have the hash value to get you there, and then you would want to see, is the username associated with this hashed password in that list? If so, then grant access. If not, deny access.
Okay, assume it's just a hash table.
Yeah,
Would the keys, the password, that would be hashed to an index that would have the value. in it.
yeah, it would have the value, that would have the username in it. So the hash is the hashed password. So user enters their password, we hash that password, and it comes up with one of these locations. And then we would search this list for your username.
And that username would point to. the-
Yeah. Exactly, that would say that the password that they entered mapped to the correct cell. That means that it's possible for you to come up with something that is not your password that also grants you access, which is why these tables are massive. Out of questions? We feel okay going in tomorrow? Little bit of work left to do, but I have a couple hours of office hours starting now. Feel free to come ask me more questions, study for a bit, come up with some questions, then come find me. I'll be around this afternoon for a bit too. I will see you tomorrow for the last exam in the class.
Also,